This question deals with an electron moving at a known speed v that goes on to collide with a positron moving at the same speed in the opposite direction, producing two photons. Part A is just asking for the de Broglie wavelength of the electron. De Broglie wavelength is Planck's constant over momentum. Now, Planck's constant does have a number to it. It's 6.63 times 10 to the negative 34th joule seconds. But my givens here are given as variables, not numbers. So I'm going to leave Planck's constant as just h. And the momentum for a particle is mass times velocity. So the answer is just Planck's constant h over mv. In part B, the electron is going to collide with a positron, which has an identical mass. And they're traveling at the same speed in opposite directions. Now, since an electron is regular matter and a positron is antimatter, when the two collide, they're going to annihilate each other and become energy. In this case, the energy is released in the form of two protons. The first thing to look at for this collision is to determine an expression for the energy of each photon. Since the electron and positron are both going at the same speed and have the same mass, they have the same energy, so the two photons they emit will also have equal energies. Since both the electron and the photon turn into energy, I'm just going to analyze the case of the electron. The electron has two types of energy. It's moving, so it has kinetic energy, which will go to the photon. Also going to the photon is all of the mass energy of the electron. So when the electron gets annihilated, all of its mass turns into energy. The formula for when all of something's mass turns into energy is E equals mc squared. So adding up kinetic energy and rest energy, the final answer for the photon's energy is 1/2 mv squared plus mc squared. Part 2 asks to find the wavelength of each photon, and for that I'm going to use the fact that energy of a photon is Planck's constant times its frequency. And since I'm asked for frequency, I'm going to use the relationship that wave speed is wave frequency times wavelength, and in this case the speed is c for the speed of light. So now I set the general expression for a photon's energy, which is h times c over lambda, equal to the electron's energy, which was turned into the photon, which is kinetic energy plus the rest energy, and then the rest is just algebra. When you do the algebra and solve for wavelength, you get this expression, and since the two photons are identical, that's the wavelength for either photon. The last part of the question asks why, after this collision between the electron and the positron, where they annihilate each other, why all that energy has to be carried by two photons. Because that amount of energy can be carried by just one photon, but in this case there has to be two, and that's due to conservation of momentum. Both particles, the electron and the positron, have equal magnitude of momentum, which is mass times velocity, but they're going in opposite directions. So I'm going to call one positive mv and the other one negative mv. When you combine these two momentums, and since momentum is a vector, you get that the total momentum of the positron and the electron before they collide is 0. In any collision, momentum has to be conserved. So in this case, there's 0 momentum before, so there has to be 0 momentum after this collision. Now, regularly in physics, when two objects with opposite momentum collide, the result is 0 momentum, which means the object is stopped. But in this case, the object we're talking about is a photon. So if a photon could stop, it would be possible for the two to hit each other and have one photon that's stationary carrying both energy of the electron and the positron. But a photon has to go at the speed of light. It cannot have 0 velocity. So in order for momentum to be conserved, we have to have two photons, both moving in opposite directions with equal and opposite momenta. So after this collision, the momentum of the system is still 0.